Hello, I'm Gary Bedard. I'm an orthotist with Becker Orthopedic. Welcome to part 3 in this series regarding alignment and fabrication and patient evaluation parameters for lower extremity orthotics. This last didactic portion will be on clinical KAFO alignment on the orthotic workstation. The first one was on the update on the protocol of determining foot progression angle and the line of progression of the knee. Second one was on knee joint center. Third one, as I mentioned, will be on the orthotic workstation. And then finally, the fourth part will be a practicum and a demonstration showing how we can take all these elements together in the setup of our positive model for fabrication of a knee ankle foot orthosis with proper biomechanical consideration, of course, essential for a stance control orthosis. So in the outline of this program, we'll have our device goal statement. We'll do a very short industrial comparison, a brief overview of KAFO fabrication history. We'll go through the device itself to show how many degrees of alignment we have for setting up your componentry. And then at the end, we'll show some video for dual hand sidebar contouring. And of course, that'll lead into our practicum. But we'll take a small break in order to set up our equipment for the demonstration itself. The goal of the orthotic workstation is to stabilize the alignment of the componentry in relationship to the positive model. The benefits we get is optimized biomechanical alignment because we separate the task sequence. We can concentrate on the clinical alignment for our improvement in protocol, and then it locks in place. That clinical alignment locks in place while you conduct your metal contouring and fabrication. We have increased fabrication speed because you're not having to reassess the orthotic knee joint axis with the anatomical axis every time you make a contour on your sidebar. And then we also have realized improved clinical performance in the orthosis because we have optimized the alignment. From automotive fabrication or industrial fabrication, we know that fixturing is widely used to hold componentry in place. In this, of course, instance, taking stamped metal components, holding them in the fixture, spot welding the components, then you produce your unibody frame for an automobile. In the internet, if you look on the web itself, there's fixturing for hobbies, such as remote-controlled airplanes where you have a fuselage that's held by a fixture for hobbyists. Same thing with bicycles. If you have a custom frame made for your body size, they can hold the various tubes that are specific to your, of course, optimal riding position, and then braze those components in place if it's a metal tube or chromoly type of frame. In our instance, obviously, the orthotic workstation was designed specifically for lower extremity fabrication, where, as I mentioned, the orthotic componentry can be adjusted so your axial centers are congruent with each other and lock them in place for your fabrication process. It ends up giving you very precise contour matching, primarily because you're coming to the same contact point every single time you make a contouring input to that sidebar. From a fabrication chronology standpoint, we have to remember that fracture bracing preceded the use of thermoplastics in the field. So consequently, with a fracture brace having an alignment fixture that had to span the patient's knee to hold the orthotic knee joints in alignment with each other for the line of progression, and then of course, hopefully in congruency with the patient's biomechanics, we would just use plaster tape and secure those knee joints to the patient's limb. So when thermoplastics came around and we were working on positive models, the fabrication fixtures used for fracture bracing found use in this updated fabrication process. Of course, clinical thermoforming started in the 1948 with some of my most recent literature's finds. But mainly it was Dana Street, 1952, that first introduced a thermoplastic cervical collar. But Gordon Yates in the UK, and then his influence here in Canada and the United States in the mid to late 60s, Gordon Yates was one of the primary pioneers in the use of thermoplastics and total contact orthoses, as they used that name back then to describe it, as a different type of orthotic fabrication from metal and leather, and having more of an open format type of orthosis, not total contact. From those early years, fracture braces on the left-hand side, that's my own collection from years in clinical practice, the different types of joints that you use for fracture bracing. On the right-hand side, you can see an ad for an older Hosmer Dorrance type of fracture brace fixture that was, of course, then used in thermoplastic fabrication. Many people would take the handheld units, as you see on the left-hand model. They would take the patella cup off of that crossbar, grind a point into it, drill a hole into the positive model, and have at least some means of securing the alignment in relationship to the positive model as you conducted your fabrication. At one point in time, Becker Orthopedic had the Scott Becker knee alignment fixture, where they used an arm coming off the crossbar of the handheld device, and you could secure that to your positive model with an oversized hose clamp, again to offer some stability to that fabrication process. We've used cast-in alignment tools. We have one product that still uses that. It's a sacrificial piece that you place inside your positive model, and that would give you the ability to maintain congruency between the joints that would fit on, obviously, the outside of your positive model. In one exercise that we used in our lab, this tool was modeled after a drill guide that orthopedic surgeons use in order to drill the hole in the femur in order to put a pone plug in. So the drill would come from the outside, have a guide, and then there would be a pointer that would fit into the notch of the femur, intertrochlear notch, so that way there, when you went from point A to point B, you knew where your exit hole was going to be in that intertrochlear notch. So it was a very precise method of drilling a hole on a positive shape here as an osseous model, but we used to use this facsimile of this device to drill ankle holes for ankle joints that were overlap ankle joints that needed a threaded rod to hold them position on the positive model. So this was a very accurate way to drill point A to point B. In the off-contouring sidebar bending that we've done in the past, all of us have placed a bending iron in a vise to secure when bending iron, and then take our sidebars off the positive model, translate that to that secured bending iron, then just use one bending iron in body English to input the bending. One of the problems that is we have to reassess your knee joint center every time you put a contour input into your sidebar. So the off-model contouring, as I said, you have that constant biomechanical assessment. It's very easy to have axial misalignment. It's a slower fabrication speed, and you have decreased clinical performance because you're reassessing that clinical alignment all the time. So as there's a fatigue factor in your technician or yourself when you're doing a fabrication process, your tolerance gets much larger at that point in time. So if you look at human factors engineering and ergonomics of how we look at research human factors and application, we feel that using a manufacturing fixture, the orthotic workstation, just has improved our speed of fabrication, our mistakes, our precision, et cetera, et cetera. It's just a more dynamic type of situation when you can have a very accurate means to conduct your clinical alignment, especially for a stance control orthosis. The orthotic workstation itself has alignment in 5 planes. You have degrees of freedom to set your knee height, your anterior-posterior depth of your knee joint placement, the mid-sagittal line that we sometimes use as a term to describe our line of progression, the linear midline, the TKA, in other words, setting that sidebar so it's midline calf, midline thigh, and hopefully aligning with your ankle joint if you're going to use a double-action ankle joint or some kind of articulation at the ankle that is connected directly to your sidebar. And then as what we've called out in the past, setting your toe out or your foot progression angle. There's a overall schematic of the 5 planes. Number 1, knee height. Number 2, AP depth. Number 3, linear midline. And number 4, mid-sagittal. So as we break that down individually, there are knobs that allow us to loosen the fixture for adjustment for every step of the process. For anterior posterior depth, for your TKA line, for your knee height, obviously, to match the knee height of the anatomical model. Mid-sagittal line, which would control your line of progression. And not unlike the mid-sagittal line we would draw on a schematic tracing to make a conventional KAFO. So there are some elements to this that translate to our foundational technical skills in creating a knee-ankle foot orthosis. Mid-sagittal line is one of them. The 5th plane of adjustment is not necessarily, or it isn't, an adjustment on the orthotic workstation itself. It's actually how you place the positive model into the pipe vise of the alignment tower, and this is established, of course, by the line of progression of the knee, and as we translate it as a measured component, setting it up for your foot progression angle. This is the critical point that we've been discussing through this didactic series. Primarily because in the orthotic workstation tower itself, there's no alignment head rotation in the transverse plane. It wasn't necessary. We can do it by just rotating the positive model in its transverse plane to set that foot progression angle, which then, of course, is determined by the line of progression of the knee. So the first step in setting the clinical alignment is mark the long axis of the foot on your positive model. And again, as we discussed in the earlier segment, the best evidence states that you're using a line that's mid-calcaneus through the second ray of the foot. So as you put your positive model in place, you want to draw a line mid-calcaneus through your second ray, and then use one of the goniometers that we've illustrated, either the two-toe or the bubble-equipped goniometer in order to put this in place. Ironically, recently I've been playing with I guess you could say a digital level that's part of an app for my iPhone. So there are different tools, obviously, that you can use in order to set this in place, including at the traditional devil level. The second step in setting the clinical alignment is to set your foot progression angle. Of course, we defined that earlier as generally being defined as an angle between the line of progression of your knee and a line representing the axis of the foot. So that offset is what we measured on the patient, and by setting it to the long axis of the foot, we then define the line of progression, anatomical line of progression of the positive model, so that way there we do have a higher level of confidence when we then come to align our orthotic joints. So here, as we see, left-hand side, again, the diagram of what is our foot progression angle. So as you put the positive model into the device, you have your line running from mid-calcaneus through the second ray. That establishes your foot progression angle, and based on that measurement with the bubble goniometer or the two-toe or even your iPhone, you now know that the line of progression of the positive model is vertical. And with that being vertical, it matches the vertical position of the joints when we finally put them into the joint hanger. So that's how we translate that skeletal measurement from our patient to your fabrication process. It's much harder to describe than actually to carry out, as you'll see in a demonstration at the end. Here it is with the two-toe. Basically, again, you've got the elastomeric component coming up over the toe, the slot to match the line you drew on the bottom of your plastic on your positive model, set your bubble level in its horizontal position, and now that you can rotate, which is what the students are doing here at the University of Pittsburgh, rotating the positive model so that the level becomes, so that the bubble is in its horizontal level position, and matching, presetting the pointer to match whatever foot progression angle they measured in the patient. So it becomes a very simple process. Doesn't really add too much time to your process. And then here's the same thing, accomplishing it with the bubble-equipped goniometer, a little bit more standard product that you can buy on Amazon, for the matter, not to be a commercial. Third step in the setting the clinical alignment is to mark your knee joint center. So as we had measured on the patient, covered that in part 2 of this didactic series, you then have a surrogate pointer that fits into your joint hanger. You can see it takes the place of your orthotic componentry, and it does come to a very sharp point. So however you've determined that knee height, you can basically preliminary set that so that your orthotic center matches your anatomical incident center of rotation. The fourth position is to mark the knee joint in its AP position. The 60-40 rule we spoke of earlier in terms of that AP depth is at always a ratio of 60-40 division, and we're using that Orthotic tool that we also described earlier as well. This is placed over the knee. It's shrunk down from an ML standpoint. The level then is put in its horizontal level position, because now that we have the positive model knee joint in the line of progression, as we put the bubble level even and make our 2 marks with the 60-40 bias protractor representing that depth position from an AP standpoint, when we mark it on both sides, they're going to be equal on both sides with the line of progression of the knee. And then here's the illustration from the pamphlet from Orthotic. Really nice tool. The fifth step in the clinical setup is to set your component knee joint in place. Our knee joint center has to reflect our knee line of progression, our knee height, our AP ratio placement, and of course the foot progression angle. Those are all the elements we're coming into place at this point to match to our orthotic knee joint. Going back to that actual visualization, it's what we're trying to accomplish. So the orthotic joint indicator comes in, slides onto the alignment bar. You put the surrogate pointer into the component mounting hole, bring it up to your positive model, and that will allow you to establish that preliminary alignment between the alignment fixture and the positive model. And this is without putting your componentry in place. So it's just a tool to help you visualize that alignment. The sixth step in setting the clinical alignment is to attach the knee joints to the component interface. The component interface, our design goal on this was to be practice-specific, not a product-specific. It does have a little bit of enhancement to fit specifically Becker joints, but you can literally use any kind of orthotic joints as long as they have a removable center bolt, and you can put either a metric or SAE bolt through it to hold it to the fixture itself. There is a slide lock on the top that is held in place by 2 Allen screws. You loosen those, the slide lock will come out of position. You mount your joint to the joint hanger using a T-bolt that has the specific threads for the bushing bolt in your orthotic knee joint. And then once you put the slide block in place, it will hold your upright so they're 90 degrees to the slide component and to the joint hanger, so that way there your uprights will lock at the same point functionally in the finished component. This will become a little bit clearer when, of course, when we run the demonstration. We do have some specialty components to match different types of knee joints as well. And as you can see, this is spacer on one of the joints. Is a load response knee joint that has a pre-tensioned external spring that is non-removable, so we had to build a spacer so we'd have clearance so we could still maintain alignment with that type of componentry. We also have some molding dummies if you're going to do a lamination, so there's different products we have in order to enhance your fabrication process. You can even do side-by-side comparison. You can slide the joint hanger from one side of the alignment bar, bring it to the other side, so if you have a change in the 3-point bend of your uprights, you can make sure that they're mimicking each other when you recontour those joints to fit the specific contours of your patient. The seventh step in setting the clinical alignment is to set your TKA, or set the sidebar so it's linear on the midline. That has a knob on the front of the fixture that you loosen so that you can have an arc swing of your componentry. Here's a little video loosening the anterior locking handle. It swings in space. So here I'm going to match the TK, make sure it's midline on the thigh, coming down trochanter to knee, locking that in place. And here you can see I would have to come back and decrease the radius of this bend with a 3-point bender in order to make my distal upright come midline to my ankle. You establish the proximal one first, and then basically, because we always bend the distal bar, this allows us to have the congruency if we're going to use a double action ankle joint in that fabrication process or that specific design of that KAFO. The 8th step is to set the mid-sagittal line. This is really the orthotic knee joint line of progression. There's a knob on the top of the horizontal slide bar where, again, you have a friction knob to loosen, so it does rotate in the coronal plane. It's not unlike the mid-sagittal line that we would draw on a tracing for conventional fabrication. So here I'm taking a straight edge, lining it up against the joint hanger. It represents the line of progression of the orthotic knee joint, and at that point in time, I'm matching the line of progression of my orthotic knee joint with the line of progression of my positive model. So it's one more alignment element, so that way when the patient bends their knee, they're both bending in the same plane and not fighting each other and creating a torque element which can add shear forces to the skin and possibly tissue trauma. Dual hand sidebar contouring is the methodology we use for inputting our contours. Of course, this comes after our alignment process, which we just ran through. You have to use balanced forces through these bending irons. It's not at all like single bar contouring. We have one sidebar bending iron secured in a vise, and then, of course, use your body English and one bending iron to input your contours. You have to balance the forces through both bending irons because the joint hangers keeping the orthotic knee joints in place around the positive model are not designed to take the input or the force of one bending iron. So you have to use two bending irons and impart equal forces. We find it's much quicker because, of course, you're not removing the sidebar away from the positive model, going off to a bending iron that's secured in a vise away from the positive model. Everything's held in an aligned position. In terms of footprint stabilization, your wrist is very much a gimbal. So if you use a handheld alignment fixture, every time you match your sidebars to the positive model, there might be a small change in that contact footprint. So it's not as precise of locking it in place and sliding away and to that contact point for every contouring input you put into the sidebar. Some practitioners even go to the point that once they've established that contact point, instead of having the sidebar coming up against an apex on the contour of the positive model, they will take a little bit of plaster away and have a flat facet at that point, because if they vacuum form plastic over that point, you've got a flat mounting point for your sidebar. So it's just another means to improve the precision of your fabrication. Because if you try to rivet, this is a problem we always face, riveting a flat sidebar onto the side of your positive model shells, you're literally riveting over an apex, and depending on how accurate you are in putting in the rivet and the sidebar, you can cant your sidebars, and then you have to go back and recontour them at the joint head to make sure they're going to be parallel with each other. The contour comparison is always the same. Your footprint is always the same, and your freehand contouring for your aluminum sidebars is exceedingly quick. So here's a little video demonstration. It shows several elements. At first, you can see I'm holding up various bending irons that have an assorted width to the jaws themselves. So I use an adjustable Cooper wrench. This is some kind called a machinist wrench or a Ford wrench or even a monkey wrench. But it's not a plumber's type monkey wrench. It's a machinist monkey wrench. You can adjust it so it fits on the joint housing itself, and then you can take your other bending iron and have a very tight radius to that first bend that you established on your sidebar, which helps you to establish the clearance between the knee joint and the patient or the anatomical model itself. Again, we can take the hangers, put on one side, and for the three-point bend, make sure that we have accurate mimicking between our sidebars. Here's the Cooper tool that we use. As I said, it's sometimes called an automotive wrench, not a machinist wrench, Monkey and Ford wrench. Henry Ford developed one version of this for use in the first production line for the Model T. And those are the catalog numbers. I have several different sizes of these, and they're a very, very handy tool. I've had one for the whole time I've been in the field. This is an overhead look to show what happens with the first bend of our sidebar. You can move the joint hanger away from the positive model in order to give you working room. Again, I have the Cooper tool, which is adjustable. I'm going to set the jaw so that it matches the width of this particular knee joint. Once I've grabbed it, then I come with my second sidebar, put my first bend in, and afterwards go back, pick up the two similar sidebars, cross them over, and then basically that S-bend will allow me to establish the clearance between my knee joint and the positive model itself. So that first bend is always a double bend. Here I'm just basically coming in a little bit more, giving a little bit more clearance, and then, of course, reflecting my second bend and going back and forth to make sure that I establish my clearance. To give you a look on the distal bar, this basically illustrates the very quick procedure of having two sidebar bending irons in your hands, and whether you put them side by side or cross over allows you to have that ability to add a convexity or a concave element to your bar. Putting up against the model, you can see that the clearance is established at the knee joint for that first touch. Once you have that first touch of the bar closest to the knee joint, you work from that first touch distally from that point in order to input your bends. You can see placing it side by side, checking my clearance, bending over. You can see I crossed over my bars and I'm here back side by side. So using that combination of either having this bending iron side by side or crossing the bending irons over will allow me to, as I said, put that convexity or concavity into the side bar itself. Contouring check. Here we can move the aligned component away from the positive model. Look at that footprint that we've now established on the positive model, and this just increases our precision of building a KAFO for our patients. We already talked about this. This is repeated for some reason, and so is this one. There is a sanded contouring fixture that is external to the tower itself. This allows you to take the joint hanger off the horizontal alignment bar without removing the joint hanger and bring the sidebar to those bending elements and then use body English. So if you're using heavy-duty sidebars that are stainless steel, it's difficult to do stainless steel with dual hand sidebar. You've got to have a lot of upper body strength. But as you can see, the joint hanger, which is this element, has slid off the horizontal alignment bar. It's still attached to the sidebar. I can place the sidebar in that bending element and just use body English at this point in time if I am contouring stainless steel. Then once you have all your contours in place, typically the next procedure is to cut the sidebars to the appropriate length without removing the joint hanger, and then drilling the sidebars on a drill press, then bringing the unit back, putting it on the alignment bar, taping your sidebars to the positive model, and using this combination as a drill guide fixture so you can drill through the holes that you already established in the sidebar, now through your plastic or composite components, and in essence that indexes the assembly. So as you take the sidebars, knee joints off of the joint hanger, and take your, at that point probably continue finishing your thermoplastic shells or your composite shells, your AFO segment, your thigh segment, as you then reassemble it with rivets or Chicago type screws. They're all indexed together, so that way there you've got accurate assembly of your device from that aligned position. Now, the orthotic workstation comes in 3 models: a benchtop, a standalone model, or I should say a pedestal mount that you secure to the floor, and of course a mobile mount. On the benchtop model, you have to have a very heavy-duty bench in order to put it on, because remember, if you're using the accessory side arm for contouring, you are putting body English into that tower, which unless you have a very heavy-duty bench, you can move that bench around by body English. The middle one, of course, is secured to the floor for stability, and then with the mobile mount, you're standing on the steel platform so that your body weight more or less adds that security to where it's standing. All right? We've also done some one-offs, because all the componentry that goes into our orthotic workstation is similar to the pedestal stand that we use for the vac station. So in my own small lab, I have it set up so I can do vacuum forming on one side and I can do metal contouring on the other side for some of my demonstration projects that I undertake. So that brings us to the end of the orthotic workstation review. At this point, we're going to switch from my didactic format, and we're going to bring in the orthotic workstation, and I'll bring all the elements in together to show you how we establish alignment between our componentry and the positive model. Thank you. Welcome back. My name is Gary Bedard, an orthotist with Becker Orthopedic. This is our 4th in the series, looking at how we assess a patient for foot progression angle, use that determinant to translate line of progression of the knee to our fabrication process. So here we have the orthotic workstation. We've already prepped it somewhat in regards to taking off the alignment head. This is our mobile mount, obviously, because it has the mobile base to it with the pedestal stand. The first thing we're going to do, as I said, the first degree of freedom in the adjustment capability of our alignment tower comes from the position of our positive model into the pipe vise. And that position is all related to the establishment of our foot progression angle on our positive model. So the first thing I'm going to do, and we're just using a generic KAFO, this is not from a patient I've seen, so I'm going to be making some generic assumptions about this positive model. But nonetheless, the first thing I'm going to do is I am going to mark center calcaneus, obviously on the heel, and second to that point is I'm going to come up and I'm going to establish what I perceive as the second ray. I'll take a straight edge and draw a line through those 2 points that we've established the long axis of our foot on the positive model. That's the first step that we want to take. I can set down my straight edge and set down my indelible pencil. I'll show 2 different techniques. I'll show one first with the bubble level goniometer. We'll make believe this patient has a 7-degree foot progression angle. My one arm will be held against that patient. The second one will be put at 7 degrees, and I'll hold that in relationship, presetting it at 7 degrees. And at this point, since my level is not horizontal, I will push or twist my positive model in the coronal plane until I have my bubble specifically in that position. Again, midline, follow the line of progression. Now my bubble is good. It's a little slow. There's a little gel in this thing. All right. I've just set it 7 degrees at this point. Bubble's level. Goniometer is at 7 degrees. There's my foot progression angle. That allows me to establish the line of progression of my anatomical model. Now that that's positioned, I can come back up to the pipe vise, and I want to secure that aligned position, representing the line of progression of my knee based on my foot progression angle. So I'm right-handed, I'll put my left hand on the shank, so that way there, as I tighten the pipe vise, I'm going to make sure that I don't have a change in that foot progression angle. So I will tighten that position, lock it in place. That was an easy one. Sometimes when you have a set screw going on a round pipe within a round pipe, it can rock a little bit. And now that's locked into place. My alternative to that, of course, is to use the two-toe. And the method of using the two-toe is, again, we have a bubble level. On the bottom, we have positive and negative for that foot progression angle of 30 degrees. We would set this at 7 degrees. Squeeze it onto your positive model on the bottom. Hold this elastic so that it is in that horizontal position. And then again, we would change it so that we would get the bubble so that it would be in its level position. Once it's level, then we would have our foot progression angle set. Again, very simple tool. Both goniometers working with the same principle of using a bubble level to make sure that we have a good reference point to do our goniometer measurement, and of course to establish our line of progression. Both elements can be used clinically on your patient, where you can use the two-toe. This is still in prototype form, whereby the baseline goniometer, you can buy it on Amazon or any of the PT warehouse sites. Make sure you order the one with the level that's built into it, and that can be used to measure both on your patient and then, of course, to translate that foot progression angle from your patient to your positive model for your fabrication. And at this point in time, we do know that we have the line of progression of the knee in its correct position based on that foot progression. So now that we've set our clinical alignment for our line of progression of our knee, we want to progress with this practicum. Take the slide the alignment head into the top of the tower. We can then put it horizontal. We'll take our joint hangers that fit on the horizontal alignment bar. Loosen the anterior set screw so that the slide hangers are going to be in a vertical position. In our parts kit, we'll take the surrogate pointers. As you can have a close-up of this. This is a little pointer with a collar on it. So as we take that pointer, it will slide into the same holes that are used to mount our orthotic knee joints. Now, I can then correspond. This positive model is already marked, perfect. As I said, we grabbed one out of the central fab here. So we'll want to loosen the bar, the knob that controls the tower itself, and start to wiggle it in place. Usually I put a fist underneath and squeezing a fist and lifting it up, getting the weight off of it for frictional forces. We can come to the point that we have alignment between our orthotic axis and our anatomical axis. All right? Now this is preset at this point a little bit. I'll just leave that. I'll back up a second because what I want to show is the use of the Orthotic bias protractor. We didn't show this in dynamic fashion on a video, but as you can see, as I shrink down my AP, it always maintains that 60-40 ratio anterior-posterior. It's also adjustable from an ML standpoint, so we can open up the width of the device. We can take it, put it over our positive model. As you can see, I'm coming over my positive model, over my foot to where my knee joint center is. I'll collapse that on my positive model, right where I've measured my knee height. Put my bubble level so that it is indicating a horizontal position. And at that point, if I were to prep myself here, at that point, I can take my indelible pencil at my knee height. I am in a horizontal position, securing that. Mark that 60-40 on this side. Keep it secured, bubble level in its proper position. Come to the other side, mark my 60-40. And so I've just set the AP placement of my knee joints on the positive model. Right? So again, just to show you the demonstration, it basically will just scissor to have that 60-40 rule. It will expand or compress depending on the ml measurement, obviously, of my patient, whether it's a peds patient or adult patient, and then collapse of my patient, and then the bubble level itself with just a $2 carpenter's line level that we put on place with a couple wire tie wraps. So an excellent tool. We use it in all the schools at this point in time. So go back to my joint hanger now. We have our knee height. I didn't measure that, but obviously it's already marked. We have a knee height. We've done our knee depth. The height is an easy one to do because you've measured it for your MTP, adductor tubercle, split the difference, and remember the origin of the lateral collateral ligament. So now we want to make sure that we are matching each side. And let's take a 1 second break. I need one more thing. All right, now that we have a yardstick, any straight edge will do. Our next step is to set our mid-sagittal line. So a yardstick is used on the medial side, just as we draw a mid-sagittal line on our schematic for a conventional orthosis, and we lay it up against the joint hanger. Because by laying it up against the joint hanger, that plane, as you can see, is represented by my motion of the straight edge, represents the line of progression of the orthotic joint. And we want to make sure that it's going to be in plane with our orthotic joint because there's that degree of freedom within the device. So if I loosen this bar, I'll swing it so it's grossly out of a line, as you can see here. All right? Grossly out of a line here. Obviously, if we tried to make a KAFO with this type of alignment, my orthotic joint would want to go in that direction. My anatomical joint would want to be in this direction. They would be completely out of sequence with each other. So our second to last adjustment, of course, is to have this midline so that their line of progression of the knee is going to match the line of progression of my orthotic joints. And we do this just by taking a straight edge, putting it against the outside flat surface of the joint hanger, moving it up and down kind of a seesaw fashion just to give us a better visualization of the line of progression of the orthotic joints and making sure we're matching that to the line of progression of the orthotic joint. The anatomical joint. We know that is vertical because we've done it with our foot progression angle. Now we know our orthotic joints are in the same plane. Lock that in position. Lock that into position. At this point, what we've done, a little in a recap, we've set our foot progression angle. That's given us our line of progression of the knee. We've set our knee height. We've set our knee depth. And we've set the line of progression of the orthotic joint. The next step we will do is we'll take our componentry and attach the componentry to our joint hangers. So I have a standard set of 1002 joints. When you disassemble these joints, you always want to make sure you mark the drop locks per sidebar because they're actually hand-tuned to each sidebar. And I have a special set of screwdrivers that I've milled the edges because the unusual feature about a Becker bushing screw is that the slot has a bevel to it. So the end of my screwdriver has a corresponding curve to it. So when I remove the screw, I always inform people to put it on a flat surface, secure the sidebar, put a little pressure on it. You never want to do the bad habit of putting it in your hand, using your screwdriver, and trying to unscrew it, because the torque might be so hard that screwdriver could slip off, and then of course you're going to end up with the crucifixion scars on your palm of your hand. And I don't think any of us are that holy yet in the orthotic field. Remove the screw. Leave the bushing bolt in the back. So I'll prep both of these. Take my bushing screw out of one side. Take my bushing screw out of my corresponding joint. We have T-bolts that correspond. We have T-bolts that correspond to the threads of our various knee joint centers. And then we want to take our joint hangers without the surrogate pointer indicating our knee joint center. We can take them off the horizontal slide bar. I'm right-handed, so I like to use my left hand to hold the joint hanger in relationship to the knee joint. You want to pass through the joint hanger with the T-bolt, loosen it, or just tighten it so there's a little friction. Flip it around. Again, I am right-handed, so I will put the slide block up against the joint. And then with the slide block in place with some thumb pressure, I will then lock in the 2 set screws on my slide block, and at that point come back and tighten up the T-bolt. What that does for me is it maintains a 90-degree angle between my upright and my knee joint and my joint hanger. So by having that slide block properly in place, when I place each joint onto my positive model, then correspondingly they are going to be locking and unlocking, or hitting the 180-degree stop at the same point. So again, want to hold it. Slide lock is already loosened. I'm coming through the joint hanger into that backer bolt with the T screw. Tighten it to the point that it's just a little bit of a friction snugness. Take the slide lock, push it up with my thumb, making sure it fits that 90-degree alignment, locking the slide lock in place first with my Allen screw, the same one from the pre-stride, ironically. Tighten up my T-bolt, and I can place that on my positive model. Now, our final adjustment is to set TKA. I'll swing this a little bit. Oop, I just moved it here. Shouldn't have done that. Have that locked in place. Look at my line of progression. Lock this in place. Let me slide this sideways just a bit. Now I want to set my TKA. So at this point, as you can see, it's pretty close. On midline here, I could probably just come down a little bit. So I want to loosen this. You can tell this is a well-used one here at the Central Fab. Loosen this a little bit. This would be my adjustment range, of course. I want it midline on the thigh. And boy, this one comes around. This is pretty lucky. You can see my offsets. Midline thigh, a midline calf. I'm coming through the middle of my ankle joint. So that way there, if I was going to run a double action ankle joint, this would be already preset. So I can lock that in place. I always want to come to the corresponding side to see if there's any offsets that I would have to do from this standpoint. And this one looks pretty close as well. So this was casted in a good position, and we're seeing everything within normal limits. So I have my line of progression and my mid-sagittal line, my TKA line of progression of my knee, foot progression angle, my AP depth, my knee joint height. So we've just run through the fabrication sequence on this. All right. So to run through that orally first, I'll fold this around. Just as a review, first thing we did, we set the positive model into the pipe vise. Once we have the positive model in the foot, the pipe vise, we drew, if it's not only already on the positive model, we then went ahead and drew a line representing the long axis of the foot, mid-calcaneus through the second ray. Once we established that, we use that long axis of the foot, then with our goniometer clinometric tool, to set our foot progression angle, which we determine from the patient in relationship to the line of progression of the knee. This is the reverse. Now we set the foot progression angle, we know that we have a line of progression of the knee. Now that I have that set, I can put my clinical alignment head in place, use my little surrogate pointers through my joint hangers, align them to our model after we've set the AP depth with the Orthotic tool, set our pointers so they match. Once we have that rough assessment, we then hung the joints on the model and made sure that we had proper TKA. So that, it takes more to explain it than it does to actually execute it in the field. So the next point we want to show is I'm going to do a couple contouring inputs into this sidebar because we saw it on video, and I'm going to make sure that we can see this through this overhead camera. Remember, your initial contours, that initial S-bend is what's going to determine the clearance between your orthotic knee joint and your patient. And that's up to your clinical intervention or decision or design parameter and the type of componentry. Obviously, if you have a drop lock, you have to have the clearances to have that drop lock fall free in space. If you have a bail lock that's an internalized bail lock, that can be closer to the patient. So your clearance on the patients are going to be determined not only by the componentry, but of course soft tissue surrounding the knee. So that being said, that first bend is going to establish our clearance. Myself, I have think that contouring is not unlike an athletic event, and in an athletic event, your athletes always warm up first. So I typically like to start with the sidebar that has the least amount of contour and work my way up, so to speak, to those sidebars that have the grossest amount or the biggest contours that you have to input. So that way there you more or less warm up to the event because it's all muscle memory when you put this in place. So I have a small version. This is my traveling version of the Ford wrench or the Cooper tool, adjustable with the smooth jaws on it. I have an 11-inch, and this you can go up all the way up, I think, to 25-inch wrenches, depending on what how big you have to get. So that first one, the jaw is closed down to the knee joint center itself. I then take my bending iron, bring my joint hanger all the way to the end of the horizontal alignment bar, put my first contour in place, put my adjustable one down, come underneath, and I always use my wide jaws, and you want to establish that secondary contour where it's going to give you enough clearance. This is going to be crossing of the sidebars, and then bend at this point. Oop, I just dropped my mic. Now that I've established that clearance, as you can see, I'm starting to bring my bar closer and closer to my positive model. Proximal end, there's a little flare. They built a flare into this. So I'm going to come way up to the end, cross my bars over. I'm going to bend this completely out of the way. My assistant sent me 3/16" bars because they felt like I had my spinach today. As you can see from the overhead somewhat, I've gotten very, very close to where I want to be. If I put my glasses on, I can actually see what I'm doing. And slide it back out. Come again as a crossover. Do a little bit of an input. Come back in. And now I'm starting to establish my contours between my positive model and my upright. At this point, it becomes repetitious in terms of executing that contouring. But the key points is I start with the simplest upright. I establish my first contact point, and I work from that point to the end of the bar. I then would come back. Since I've already had one bar established, I would then pick up my indelible pencil. I would draw a line to give me a reference at that point, because sometimes a bending iron might slip. I could fall out of alignment. This gives me that checkpoint that my contact point is always coming back to the same point. So once I've established one bar, I then work with the distal bar, same thing. Bend it in, S-turn, establish a contact point. So now I have the contact point above, contact point below the knee joint, and then on that particular distal bar will then continue to bend until I get to my end point of my design. And my end point of my design at this point would be to determine whether I'm going to have a solid ankle AFO, whether I'm going to have an articulated AFO. If it's going to be articulated, do I have to match the sidebar to a double action ankle joint? Or if I'm going to use a Tamarack joint or an Oklahoma joint or an accessory ankle joint that's not connected to the sidebar, then I'm going to terminate my bar so I have enough room in order to mount that componentry after I do my contouring. Typically at this point in the standard of practice, most folks vacuum form their plastic first, then they do their contouring at that point. This is compatible with that. If you want to put the bars inside, you can contour first, cut the bars or make dummies, mount them to the model, vacuum foam after that, and come back afterwards. So it's open to the different interpretations that we have of fabrication. As I mentioned, at the end, when you have your bars all contoured, you can then slide the entire joint hanger and sidebar off of the horizontal alignment bar, go back. As you can see, at this point, to make my fabrication quicker, I just bent the distal bar out of the way to give me clearance with that flare on the proximal thigh. Distally, I would have done the same thing to clear my malleoli or any plaster interference to have the contour lay against my positive model. I then would cut the bar, drill the bar, come back and put it back into my alignment bar. At that point, I would take a drill through those holes, and that would index my plastic components to my sidebar. So that way there, when I finish my trim out, I could assemble everything with the Chicago screws or rivets, and everything would be indexed together. Okay, so that would bring us to the end. So in essence, that would act as my drill guide in order to finish my componentry. So that brings us to the end. We didn't bend the sidebars completely because we were concentrating more on obviously the alignment criteria, but we would continue that same process with the 4 bars, and your timing is at least 2 or 3 times as quick as using a handheld device. All right. So one more time, I'm going to run through what your sequence is. Number 1, positive model goes into your tower with the pipe vise. Number 2, you would draw, if it's not already on the positive model, your long axis of the foot. You would then use the bubble goniometer or the 2-toe, if that ever comes to market, on the device to set that foot progression angle. That now has established, so our positive model has a vertical line of progression, matching the vertical line of progression of the joint hangers for our tower. Next, if your knee joint center is not marked, you would mark your knee joint center for your height. You would then use the goniometer that sets the 60-40 positioning for AP on your model. So you'd have your height, you'd have your depth. You would then take your joint hanger with the surrogate indicator, align your joint hangers with your anatomical centers At that point, your next step, you would mount your componentry to your joint hangers, put them in place. Forgetting one step in there, you would use your straight edge first. Some people use the sidebars as your mid-sagittal line. I like to do it before I might mount my componentry and just use a straight edge for that mid-sagittal line, which establishes the line of progression of our orthotic joints to the line of progression of our positive model. Mount your componentry in place. Then it would be TKA line. Remember, if we do a TKA line, if it's a gross adjustment, in other words, if I swung it in a very gross manner like this, that would move my orthotic joint distal and anterior to my anatomical joint. If I swung it in this direction, it would move it proximal and anterior. So if that's a gross movement because of the offset of your mid-sagittal line, because your mandrel might be crooked, the way that the mandrel sits in your positive model might be not linear with the long axis of your positive model. You might have a grosser adjustment than what we demonstrated here. So consequently, you would make an adjustment. If the arc swing was so large, you would then put it more posterior and distal to match your joint, or posterior and superior to match it if we swung it in the opposite direction. Just be aware this is an arc segment, and it can change your mechanical axis in relationship to your anatomical axis, and you might have to accommodate that. All right, so that would set your TKA. Once your TKA is set, then you would basically start your contouring. Again, the proximal medial upright is the one that has the least amount of contouring. I start with that one first to warm up my muscle memory, and then progress with the distal bar. Then I go to the lateral side. On the lateral side, again, I usually start with the proximal bar, establish my contact point with that first S-bend for the clearance of the joint, continue with my contouring from the knee joint to the proximal part of the bar, and then do the distal bar. And at that point, cut the bars, drill the holes, index it, drill the plastic components, and you can put everything back together. All right? So I hope the Orthotic Workstation was the first product that I developed for Becker Orthopedic back when I was a project manager of R&D. Came out in, I believe, 1994. We did quite a bit of work on it. We've used it in our lab since then at Becker. All our techs basically have come to accommodate this. They would not want to fabricate without this device anymore. Many of your MSPO programs now, we're teaching this in the schools, and I also have it at Strathclyde in Australia and South Africa, Kuala Lumpur. So a lot of your practitioner programs around the world are using this device. It's the only KAFO fixture in the world at this point in time, and it corresponds to the vertical jigs that we, of course, the Hosmer type of jig that we use in prosthetic, and some of the other vertical jigs that we have for prosthetics. So it's become the only one for KAFO fabrication. And with our move to stance control orthoses, where it's so critical to match the alignment of your limb to your device, because we don't have the adjustability in terms of doing dynamic gait adjustment through our components like you have in prosthetics. You have to build the accuracy of your product into the device during your first fabrication exercise. It's very difficult to change afterwards, okay? So this was the last part of 4 segments today, 3 didactic, 1 practical. I hope this helps everybody that does a little bit of mental bending. I've done thousands on these things. I think about 6,000 at this point in time. I don't anymore, but at one point did a lot of mental bending, and I find it to be an invaluable tool. So thank you for your time today. My contact information is always at the beginning of these programs, so if you have any questions, feel free to get in touch with me. And again, I thank you for your attendance at this point. Thank you.